Hello and welcome to the heat transfer course for convection. My name is Wilko Rovs, and in this video we will look at the topic of forced convection in internal flows, as we have done in the last video as well, but with a special focus on the logarithmic mean temperature difference, LMTD. The learning goals as described. The learning goals are as follows. First, we will look at the knowledge and the meaning of the logarithmic mean temperature difference. And then we look how to apply this temperature difference and how to calculate this. To introduce the logarithmic mean temperature difference, we will start with the same kind of flow configuration. We have a flow going in here and we have a heat flux coming from the sides, but instead of prescribing a heat flux as a boundary condition, we now start with a constant temperature at the wall. To calculate now the temperature distribution along the axis, we do a similar energy balance as before, and we can see that this energy balance is quite the same as it has been before. We have an ingoing enthalpy flow, we have an outgoing enthalpy flow. We assume that the velocity is quite fast, so that diffusion does not have a significant role in axial direction, and we have an ingoing heat flux from the sides. So the energy balance is 0 is equal to all the three fluxes. To define the three fluxes, we have the enthalpy flows, the mass times the heat capacity, so flow of heat capacity times the average temperature. We know from the last video this Tm is the caloric mean temperature as introduced before, and on the outgoing flow we have just the temperature at the location x plus dx. Now for the ingoing heat flow we have something different because we don't describe the heat flux itself, so the ingoing heat flux is equal to a heat transfer coefficient alpha times an area times the difference between the wall temperature and the mean temperature. The area now here for this infinitesimal element is the circumferential area of the pipe, so P times D times the infinitesimal element dx. And we can see we have here a dx, and we know from Taylor's series expansion we will get here a dx, and this will cross out. I will not go into the details. I think this is something which we all know from the conduction lectures already. So we end up with a differential equation. So we have here the change of the mean temperature over the length of the pipe is then equal, if we put this on the other side, to the heat flux that is going in here. So alpha times pi d times the wall temperature minus the mean temperature at the location x. We can bring this over to the other side. Now here we have the differential of the mean temperature, but unfortunately we have also the mean temperature in here. So we see that we have an inhomogeneous differential equation for which we can apply again the knowledge from the conduction lectures with the introduction of other temperature here of the temperature theta, and we define theta in a way that it's equal to the mean temperature minus the wall temperature. And in this way we can see here, if we have theta, we can replace theta in here. This will simply become theta. And if we take the first derivative of theta and the first derivative of this expression with respect to x, then the wall temperature drops out and we have exactly the term, the differential of the mean temperature with respect to x divided by the spatial coordinate. So we can plug in the definition of this new temperature, and we get here the derivative of this theta dx is equal to minus theta times a constant. Now, separation of variables, bringing x to the other side, bringing theta to the first side, we have the differential equation that we can solve, and here we end up with the linear part, and here we see that we have something logarithmic. So the integration will lead to the ln of theta is equal to our constant times the linear part x, plus a new integration constant, which we call c. Now, bringing this in a form that we have an explicit expression for theta, we have to integrate this on both sides. So change the ln, not integrate, but change the ln. So we get here theta is equal to the exponent of the expression. And this we can, instead of the constant c as an argument in the exponent, we can write this in front. So we have c star times the exponent of a constant times x. We can see that the temperature will follow an exponential function. Now, what about the constant c star? How can we calculate this? First of all, we can bring this back to our Tm. So we change theta to Tm minus T wall and have an explicit expression for Tm, which is then c star times the exponential function plus the wall temperature. Now, the boundary condition at the location x equal to 0, we have the inlet temperature. If we use this, we can see that the c star is simply then given in a way that we finally get T in minus T wall. So we have now a nice explicit expression for the mean temperature depending on the inlet temperature, the wall temperature, and the heat transfer coefficient. Now, for the outlet temperature, we just have to evaluate our function at the location L. So we end up with an explicit expression for the outlet temperature. But you can see we have here the outlet temperature, and it still depends on the heat transfer coefficient alpha and this whole part here. We can replace this. Let's have a look how we did this. So on the one side, we have to take the logarithm of both sides. So here on the left side, we get an ln of the expression, and here the exponent will drop, and we have brought together the pi dl, which is the total area of the surface, so alpha times A divided by the flow of heat capacity. Now, the last step that we can do is we can change here flip the signs. So here the mass and heat capacity are on the top, and on the other side we have 1 over this logarithmic expression. This is one part that we need to calculate the logarithmic mean temperature difference. The other part is that we want to calculate the total heat flux that is transferred from the wall towards the liquid, or vice versa, with a driving potential. So we relate the total heat flux to the heat transfer coefficient times the area times a required driving potential. This describes the driving potential necessary to drive the total heat flux over the surface. So this total heat flux is nothing else than the difference between the ingoing and outgoing enthalpy flow. And we look here, as it's written here, the total heat flux from the fluid to the wall. So the fluid that is transferred from the heat that is transferred from the fluid to the wall will be H in minus H out. Now, what is the driving potential that describes this? We have talked about it. We are looking at this delta T. And so we can get an explicit expression for delta T by introducing the ingoing and the outgoing enthalpy flows, describing this with the temperatures, the ingoing and outgoing temperature. So we have here an explicit expression. What we see directly is that this expression here with m dot Cp divided by alpha times A is exactly the same that we have on this side. So in the next step, we combine these two equations. And to do so, we also do some kind of sign flips. So as you can see here, we have a minus at T out and T in. We can drop this minus and change T out and T in. Now we can look at this expression here. It's made green because we also introduce this here. We change this a little bit. We bring the m dot Cp divided by alpha times A, because it's the same expression as here, to one side. And on the other side, we have delta T divided by T in minus T out. Combining these equations will give us an explicit expression for the delta T, and this we call the logarithmic mean temperature difference, because we see we have here a temperature difference and here also this logarithmic temperature difference. The difference T in minus T wall and T out minus T wall, we can also use this here. We just write T in minus T wall minus T out minus T wall. So one's minus T wall, one plus T wall. So we can combine this in delta T in, which is then T in minus T wall, minus T out, which is T out minus T wall, divided here on the bottom also T in minus T wall and T out minus T wall. This is called the logarithmic mean temperature difference. What is the purpose of this logarithmic mean temperature difference? So first of all, we can use it as a driving potential for calculating the total heat flux if we know the heat transfer coefficient and the area. And of course, we need to know the inlet and the outlet temperature. So when can we use this logarithmic mean temperature difference? It is often used in the calculation of heat exchangers. Requirements are, of course, that the heat transfer coefficient alpha is constant and that the specific heat of the fluid is constant, so there are no temperature dependencies in the fluid properties. The wall temperature is constant and the mean fluid temperature changes over the length. So this is the internal flow configuration, and of course the problem is stationary. So often this equation has to be used iteratively because there are two unknowns, the outlet temperature as well as the heat flux. Finally, in this video we end again with a question of understanding. So what is the meaning of the logarithmic mean temperature difference and when do we apply this? I think we have shown this already in the last slide. The meaning is that it describes the driving potential for the heat flux in case of a constant temperature at the wall. And we can apply this, of course, in internal flow configurations if we have, so for instance, a pipe flow or a flow between two plates. Thank you for your attention.